Let's try solving pH problems using a calculator. So in many of the examples we did earlier, we had simple numbers like this one. Let's look at this one as a review. So we have real plus concentration of 5 times 10 to the negative 8th. So we saw before that if the numbers are simple, in fact if we have ones, like this problem, in the coefficient, that number of the exponent ends up being the pH. We just change the sign. Well, if we don't have a 1 for the coefficient, we'll need to use a calculator since it's not quite so simple. Now, it is a powerful understanding, though, that that exponent is a good estimation of the pH. We know that the pH is going to be somewhere around 8, but to get a more accurate value, we'll need to calculate this using the calculator. So, pH is the negative log of the hydronium ion concentration. And so it's very simple. Just plug in the numbers. The hydronium ion concentration is 5 times 10 to the negative 8th. So on this calculator, I would do 5e8 negative, and then press the negative positive sign down here at the bottom to make that a positive value. Alright, so here's my answer. Now, significant figures can be a little confusing. The power here is coming actually from an exact value. So when we look at significant figures, we are only going to be looking at the number of places in the coefficient. This represents the measured numbers. So we actually have just one significant figure here, and so 11.3, we're going to round that. Our first number, the 7, corresponds, this number corresponds to the exact number here. So that's exact. And the 5 coefficient tells us how many decimal places we get to round to. We'll round that to 7.3 since we have just one sig fig in the coefficient. So 7 is our answer. So in terms of sig figs, the number of sig figs of the coefficient determine the number of decimal places. The exponent is considered exact, and that translates to the first digit in the pH number. Let's try this problem with the other style of calculator. So we have, in this calculator, we go negative and log 5 second -8, close parentheses. Good, we get the same number, just like we should get. What is the pH of bleach with this concentration? So if we have H3O plus that's 4.2 times 10 to the negative 12 molar, and we want to know the pH. We plug into the equation. pH is the negative log of the hydronium ion concentration. So the pH then is the negative log of 4.2 times 10 to the negative 12. You can use a calculator. 4.2 E12 negative log negative. So that's 11.376. Let's look at how. Now, like we said before, the 12 will correspond to the first digit before the decimal. So this 12 corresponds to the 11 here, and those are exact. Then the two digits in the coefficient correspond to the two decimal digits that we'll include in the pH number. So we have 11.38. So we can figure out the pH using the formula. We can also work the other direction, and we can find concentration, like in these examples. If we have a pH of 8.25 and we want to know the concentration, we just work in reverse. So the pH is the of the hydronium ion concentration. So to find, if we know the pH and we want to know this, let's move that negative sign over. And we have this expression. It's base 10. So 10 to the negative pH power is the hydronium ion concentration. So the pH is 8.25. 10 to the negative 8.25 is the hydronium ion concentration. Well, let's put that into our calculator and get a number that's in scientific notation. So we use the inverse log, or 10 to the x key. So on this calculator, I would type in 8.25 negative second inverse log, and I'm going to convert that to scientific notation. Second CI, that's 5.62 to the negative 9. So the H3 plus concentration is, now let's those sig figs. We had said before that the exponent corresponds to the number here, and then the number of decimal places corresponds to the coefficient. So the number of decimal places in the pH value corresponds to the coefficient. So in this case, the coefficient can have two decimal places because we have two places here. So 5.6 is what I'll round this to. 5.6 times 10. Now the exponent on the 10 corresponds to the exponent here. So the -9. So the 2 decimal places correspond to the 2 decimal places in my answer. And the exponent matches or corresponds with the number of places in front of the decimal. Let's try this other example as well. What if we had a pH of 9.5? Well, we use the same process if we want to know the H3O plus concentration. Since the pH is the negative log of the H3O plus concentration, we just need to take the inverse log of 9.5. Let's try that in this other calculator this time. So keep in mind, though, as with the last example, you're going to have to put in a negative value. So since we solve this is base 10, move that negative sign over, and we have 10 to the negative pH is the H3O plus concentration. 10 to the negative 9.5 is the H3O plus concentration. So we'll need to make that number negative based on the formula here as we put in the inverse log. So we have 9.5, or this calculator we use a different order, so we do log first. So we do second inverse log, negative 9.5, close parentheses, and we have 3. 3.16. So this one is 3.16 to the negative 10. 3.16 times 10 to the negative 10th. Let's write that again. 3.16 times 10 to the negative 10. Capital M. Let's look at how we can find other values here, like pH from OH. What is the pH of an ammonia solution with an OH value of 3.7 times 10 to the negative third molar? Now we've seen that there are a few relationships that we can use to solve these problems. One relationship is the ion product constant of water. Kw is the H3O plus concentration multiplied by the OH minus concentration, and that value is equal to 1.0 times 10 to the negative 14th. So that's one way we can solve this problem. We can plug in the concentration values, use this, and find an unknown concentration. We've also seen that the pH plus POH is 14. So we can use these two equations to relate the OH and the pH. So if we have OH minus, let me show you two ways to do this. One way is using the ion product constant of water. So we have OH, that's 3.7 times 10 to the negative third molar. We want the pH. One way to do this is with the ion product constant of water. We're going to say Kw is 1.0 times 10 to the negative 14th, which is the H3O plus concentration times the OH minus concentration. So we can plug in our unknown here and solve. So therefore, the H3O plus concentration would be 1.0 times 10 to the negative 14th divided by the OH concentration. Plug in our numbers, and we get 1.0 times 10 to the negative 14th divided by 3.7 times 10 to the negative third. And so that comes out to 2.7 times 10 to the negative 12th. Now we just need to take the negative log of that value. So the pH is the negative log of 2.7 times 10 to the negative 12th. So that gives us a pH of 11.57. That's one way to do this. Let's try another way. So the other way is to use the idea that pH plus POH is 14. So first I'm going to take this and find the POH is the negative log of the hydroxide ion concentration. So the hydroxide ion concentration we were given is this number. So it's a negative log of 3.7 times 10 to the negative third. So the OH is 2.43. Now we can plug that in. Since the POH plus the POH is 14, take that idea and we have pH plus POH equals 14. So the pH plus 2.43 equals 14. So the pH then is 14 minus 2.43. So the pH is 11.57. Two ways to do the problem, end up with the same answer. So we can also use that idea to solve problems like this, of course. This is much simpler, since in this case we already are starting at pH. It would be easier to use pH plus POH equals 14. So that one's just simply a matter of subtracting the pH 14 minus 3.5. So we get a pH of 10.5. And we can continue those types of problems if we have something like this. We can just work from the pH to the concentration as needed to solve these problems.